Yeah, the next talk is by Alessandra, talk about worst case to average case hardness of LW.
Okay, thank you. So here's the third talk in the series that Daniela mentioned. So today I'll be talking about the hardness of LW under an alternative perspective, and this is joint work with Devesh and Leong Jingmin. So just to reiterate, why do we care about LWE? It's an average case problem that's at the basis of a lot of crypto systems, and not only that, it's robust and versatile. And moreover, we know how to reduce worst case problems to LWE. And for this reason, we know that the random average case instances that we have, that we use in practice for practical cryptographic applications, they're just as hard as the worst case instances we can come up with. So what are these worst case problems? Specifically, they're lattice problems gap, SAP, and BDD, which I'll define later on. And moreover, because we don't know of any efficient quantum algorithms that can solve these lattice problems or LWE, this makes the crypto systems based on LWE post-quantum, for now at least. All right, so let me define LWE formally. The input is just a bunch of polynomial number of noisy samples consisting of uniformly random vectors and its noisy inner product with a fixed secret vector. And for the search variant of LWE, the goal is to output the secret vector S. So you can think of this as being given a very tall, uniformly random matrix and its perturbed inner product with its perturbed product with a fixed secret vector S. So the decision variant is actually what we use for crypto systems. So here we're given a bunch of noisy random samples, and our goal is to determine, okay, are these samples actually from LWE, for an LWE distribution determined by some secret vector and error distribution phi, or are they truly uniformly random? Okay, so I'm just going to review, because the previous talk also talked about this, but in a lattice is just a discrete set of points in Euclidean space that's generated by a linearly independent set of basis vectors. And a lattice can have many bases. So one central problem for lattices is the shortest vector problem, and here we're given a lattice basis. It can be really ugly, really long vectors, and the goal is to find the shortest non-zero lattice vector, which is not unique. And gap SVP is just an approximate decision variant of this. So this is what we'll be talking about today. And again, just to review, because the previous talk defined this, but the bounded distance decoding problem is another important problem where we're given a lattice basis and a target vector that's guaranteed to be close to the lattice. It's a target vector in Euclidean space. And our goal is to find a lattice vector that's close to it. Okay. So going back to the reductions, from worst case problems to LWE, Regev, when he introduced LWE as a problem, he showed a quantum reduction from gap SVP to BDD, and then a classical one from BDD to LWE. Piker later made this reduction fully classical, but this blew up the modulus in LWE to be exponential. And then later, Brakersky and al. Made this entire reduction classical with polynomial modulus. So this is the full picture that we consider today. So all the way from gap SVP to LWE. Okay, now let's look at algorithms for these problems. So for gap SVP and BDD, the fastest algorithms we know run in about 2 to the theta n time for polynomial approximation factor. So I think Aparna mentioned some earlier. Okay. And so let's see what this reduction tells us about LWE algorithms. In particular, if we assume that the known algorithms we have for these lattice problems are the best possible, then what this reduction says is that LWE cannot be solved in less than 2 to the root n time. Right. But we know of algorithms that can solve LWE in 2 to the n log p over log n time. So there's a pretty big gap between these two. So from this perspective, this chain of reductions that we know of is pretty lossy. Right. So what we do today is we close this gap by changing our perspective a bit. Okay, so just to reiterate from the first two talks, what does it actually mean for crypto system to be 256-bit secure? This is the question that we're centering all this around today. So there's no universal conventional notion, as Daniela mentioned, but these are the two main contenders that seem to be used. Either the fastest algorithm we have for breaking the crypto system requires at least 2 to the 256 time, or no efficient algorithm can break the crypto system with greater than 2 to the minus 256 probability, right? But in practice, for practical applications, we don't care about 2 to the 56-bit time. We just care about 2 to the 60 maybe. That's longer than the age of the universe. So given that usually our cryptographic security models are based on limited computational power, then B is usually what we want, right, for practical applications. So this is the perspective we take. In particular, we measure computational hardness by considering the maximum success probability of any efficient algorithm that can find a solution to the problem. Okay, so we actually managed to study worst case to average case reductions under this framework. And this is what we do for LWE. So if we look at the success probability of solving LWE using a trivial algorithm, just guessing the error randomly, then you can get a success probability of p to the minus n. And all the other algorithms we know of are not efficient, so we believe it's unlikely we can actually achieve better than this probability. Now for the lattice problems, we can get a success probability of 2 to the minus n squared over log n just by using LLL or the slide rule with guessing coefficients. And all the known techniques that we have don't seem to improve this probability when we restrict it to efficient algorithms. So it's actually unlikely we can achieve better than this, or much better than this. And because of the close relationship between BDD and gap SCP, where their approximation factors are polynomially related, it's unlikely, we can also conclude that it's unlikely we can achieve better than the known algorithms that we have. We saw some specific algorithms in the previous talk too. All right, so this leads us to make a natural conjecture that no algorithm can solve BDD with inverse polynomial approximation factor with success probability better than 2 to the minus n squared over log n time. This is based on what we know. Okay, so here's what we show. So again, the trivial algorithm gives us b to the minus n success probability for solving LWE efficiently. And using our conjecture, we show that under this new framework, the maximum success probability of efficiently solving LWE gives us a lower bound of p to the minus n over log squared n. So we close this gap. This is a much tighter lower bound, right? So let's look again at why the original reduction is so lossy. In particular, a couple of the branches make polynomial many calls. And why is this bad for us? It's because it causes an exponential loss in success probability. So I'll show you why. But let's forget about that reduction for now. But if I have any reduction from problem P to problem Q, that makes K oracle calls to Q, to the solver for Q, then if I have a lower bound of epsilon on the success probability of solving Q, then for P, this probability increases by K exponentially, right? So just another way to write this is using an upper bound on P, and then this decreases exponentially for Q. Okay. So in order to even get a meaningful conclusion, like under this framework, we need to limit all of our oracle calls to be just constant. So that's what we do. We make a single oracle call in every single step of this entire reduction, and this just gives us a polynomial loss in success probability. So, and just to mention, we use the same techniques as the previous works have done, but it's not as easy because we had to take great care to make the success probability of the loss like very explicit, and also to limit the number of oracle calls. So it's a bit of a delicate balance. Okay, so this is our first main result, that if no BPT algorithm can solve BDD with success probability greater than 2 to the n squared over log n, then no efficient algorithm can solve search LWE, like even for binary secret with a success probability 2 to the minus n over log n. So I'll show you a little bit of our techniques that we use to prove this. So for the first reduction in this chain, it's just a trivial algorithm from BDD to a modular version where we're interested in finding the coefficient vector on modulus, some p. And here we trivially just blow up the modulus, and right, then this like just gives us no loss in success probability whatsoever. Now for mod BDD, we go to a generalized version of LWE where we don't know the error distribution phi, we just know it comes from a family, D. So here we just generate discrete Gaussian samples and use them to generate LWE samples, and this gives us a slight additive loss in success probability. And then from general LWE to LWE, we carefully sample Gaussian noise in order to guarantee an optimal success probability, and this gives us another slight multiplicative loss. Okay, and then for the remainder of the reductions, we use the techniques from Bakursky and al., and this preserves success probability throughout. So the loss comes from the second two. Okay. So we also prove a second result relating search LWE to decision LWE, which I won't go too much into today, but basically if no algorithm can solve search LWE with success probability alpha and expected polynomial time, then no efficient algorithm can solve decision LWE with probability close to alpha. So I say solve in quotations because we have to be very careful, as the first two talks mentioned, how we define success probability for decision problems, for specifically random-looking decision problems like LWE. Okay, so just some future directions to keep in mind. It'd be interesting to find a similar result from gap SUV to BDD, because we only showed from BDD to LWE today, and we don't think it's possible, but it'd be interesting to actually prove that it's impossible. And then the two reductions I mentioned that we proved from BDD to search and then search to decision LWE, these are disconnected. And this is because in the second half, expected polynomial time is a fundamental part. So in particular, we use Goldreich-Levin and a generalization of those techniques. So is a workaround possible for this? And also, we're also trying to promote this framework, but is it possible to use the similar framework like with the practical applications in mind to study the complexity of other problems that are relevant to cryptography or learning? So we just did it for LWE. Okay, so any questions?
Questions?
So I'm not sure about the first problem. So isn't gap SVP and BDD known to be equivalent up to a square root of 2 factor? I mean, there's a paper of me and Vadim from 2009 giving reductions in both directions for worst case problems. That's what you're talking about.
Yes, but I'm not sure like what the connection is between the success probability of both, because in that reduction I know they make like it's dependent on iteration. Okay. So yeah, I don't know if. Yeah.
They make multiple calls. So okay. So the question is whether one can give a many one reduction. Okay.
Yeah. So it's not about the reduction, just the
Okay. If no, coffee break.